Okay, Jaden, we are live.
All right.
Ooh, we got 0 viewers because we started a minute early. Okay.
All right. Let me.
Shut this door.
Okay, so we have, since last time we started streaming, Kip, we have 1 or 2 more subscribers. That's so
I
exciting.
know, dude. So exciting. But for some odd reason, they're not popping up as saying that they subscribe, so we can't, make some beautiful notifications.
Okay.
But so anyways, for all of you guys that are joining us tonight, all 2 of you, woot woot, please feel free to send us any questions that you have. You can send them in the chat, or you can send them to our email. But if no one has any questions, I have a math problem that I've been trying to work on, and so me and Jaden are going to continue to struggle through that. So if you want to watch us struggle through a math problem, you can do that, or ask any questions that you would like. Okay, so the math problem that I am struggling with goes like this. P adjusted, okay, is equal to P adjusted over 1 plus beta, and then we've got T for temperature minus RC. And this is equal to E, which is the irradiance of the sun, A1, that's subscript, we don't want that, A1 E, no, stop, no subscript, A2. Oh my gosh, you guys are smart. Thanks. Oh wait, there's no E there. It's just A2. Okay.
Kip, will you do me a favor and make a list
Of what these mean?
What everything means, just so I have a better idea, and so anybody watching can at least know what they
I'm gonna put it
mean.
on a sticky note for you.
Okay, sounds good.
J is power adjust. Oops, except it just made mathematical or something show up. Solved. Oh yeah. I can't spell very good. Come on. Apparently I can't hit enter with a sticky note. P act is, dude, things just keep popping up. Solved keeps popping up over and over. Maybe I should freeze these, hide them for a second while we keep. P act is power actual. And then we got T is temp, E is irrad. And RC and beta are just constants. Okay, there we go.
Impressed you can write that equation.
Okay. It's not beautiful,
Okay.
Jaden, but it will do. Alrighty. So, Jaden, I'm going to give you a little more historical context about this, if that's okay. So,
Yes.
normally, Jaden, when you're looking at a solar array, you can do something, which is, this is your irradiation, okay, irrad, and this is in watts per meter squared, and this is your power of the solar array, and this is in watts, okay, or kilowatts or whatever, but it's work, power, right? And then normally, Jaden, you get something like this as the solar array produces. You get this kind of linear trend, right? It makes sense. The more power or the more irradiation coming in from the sun, the more power you get, okay?
Right.
But what happens is, because these solar cells are dependent on temperature as well, you can get something like this happening, where the line kind of shifts depending on how much power or how hot the solar panels are getting. Okay?
So if the solar panel gets hotter, you have less power?
Yes, they become less efficient.
Okay, because they're giving off a lot of the energy that they're getting through heat.
Sort of.
It
It
is,
actually,
or
I think it has more to do with just the properties of solar panels, and they just don't work as well the hotter they get. The differential between I think it's a PN junction or NP junction or whatever. It's a diode, right? And so as they get hotter, that difference, that potential difference, actually gets smaller, I believe. I could be wrong on that, but that's something that happens. So they just become less efficient the hotter they get. Okay.
okay.
But Jaden, there's something that's very important right here. Notice how everything, when the irradiation is zero, no matter what, is at zero, right? The power is at zero when the irradiation is zero. That makes sense, right? If you've got no light coming in, then there should be you got no energy coming in, you should have no energy coming out, right?
Right. I agree with
But,
that.
so my first concern about this equation is this part right here. This is simply, if we look at it, right, it's essentially a line, right? mx plus b.
Okay.
Well, according to this graph I just drew here, our b should be equal to 0, right?
Okay.
You seeing that?
Yeah, that makes sense.
Okay.
When we have 0 coming in, we should have 0 power coming out.
Right. So when
So
x is
it wouldn't
0,
make sense to start at 10 power,
that's
because then you would not. Yeah, that makes sense.
okay. So the next thing is, so therefore we should say that a2 is equal to 0, right?
Yeah.
So this part of the equation that is written should not even exist.
Yeah, that doesn't make sense to have a y-intercept in this situation.
Does it, right?
No, it doesn't.
Because here's the other thing, right? If there's no, and so we can look at it even further, which is the actual amount of power that's coming out of the system. If it's 0, then our irradiance should also be 0, right? So
Right. And
if
the
power is 0,
irradiance,
if we have 0 over, this 1
yeah,
plus beta, right, t minus RC, it shouldn't matter, right? It doesn't matter what our temperature is or anything. It's still going to be 0.
right.
And in that case, according to this graph, our irradiance, if we left this as plus A2, our irradiance in this case should also be 0, right? So essentially what we'd get is we'd get 0 equals A2. So again,
So
that's proving that
A2.
point, right? If A2 equaled anything but 0, this statement would not be true.
Right. Kip, are there any situations where you have the constant RC greater than the T?
Yes.
Okay, so
So that RC is a reporting condition. It's like a temperature that's decided on, from what I read, by people. And so it's just the difference between the temperature decided on. Also, B, I'm pretty sure, is less than 1, if that is helpful at all.
B is less than 1.
So if
Okay.
So if T is less than RC, anyways, the bottom is never going to go negative, I believe, right?
If you have...
If beta is less than 1.
It could still be negative.
Could it?
Yeah, just put in, if B was like 0.5 times
Oh yeah,
negative
okay.
2, right? You could still get a...
Right, yeah, you could get to a negative.
Do they
So,
restrict the domain?
well, I mean,
Because it doesn't...
T
How
has to
would
be
you
an
ever get
actual
an...
T has to be an
Yeah.
actual legitimate temperature. So, and this is in Celsius, so if we're talking, like negative, I don't know, 500 degrees or something, that's probably not going to happen.
Right.
Okay, so that's step 1 of the confusion. Jane, we're up to 6 viewers. Anyone got any questions or comments on what's happening, or want to learn something different than what we're talking about? Go ahead, let us know.
With the irradiation, or is it irradiance?
Irradiance is probably, yeah, that would be a better word, thanks.
Okay, but just to clarify, irradiation is kind of like the intensity of the sun per surface area.
Right. Irradiance,
Right.
yeah. Irradiance, yeah. That's the right word.
Okay. And so basically, if you have the sun and your solar panel angled at a really good angle, you're going to be getting a stronger intensity, right? So a little bit more irradiance. And if you put your solar panel in a shadow, you're not going to be getting very much intensity or irradiance. So that's just kind of to clarify those words and what they kind of mean.
Yeah, thank you for clarifying. Okay, so let's go ahead now and talk. Yeah, keep going.
Power adjusted. What does that mean exactly?
So
if you have...
Sorry, keep going.
Go ahead.
So the power adjusted would essentially be like this line, I believe, Jaden. So like if we said this middle line, right, is kind of like as if temperature didn't exist, or at a perfect reporting condition in which the modules are rated kind of and tested at a specific temperature. And so when they say something like it's a 400 watt solar panel, it means that it's 400 watts at, if there's I believe it's when there's 1,000 watts per meter squared irradiance, and the temperature is at the specific temperature RC, I believe. But then, you know,
Okay.
so if your temperature is changing, it's going to change this irradiance versus power line, right?
Right.
And so the power adjusted is kind of like what the manufacturer claims that their solar panel should be acting at.
Okay.
Okay.
So really, we shouldn't have equal signs,
Why
right?
not?
If someone's claiming to have this, but we actually test it, it's not gonna always be
That
equal to that, right?
well, that's why. So this is the equation states that the power actual divided by this, right,
Should equal the
should
power
equal
adjust. Okay.
exactly. But this is
Okay.
where so this is where my big complaint is coming in, right? Well, this graph right here shows that the power is a function of irradiance, right? This E.
Right.
So this top part here should be a function of E, okay? But the problem is then we have down here,
The function of time.
or that's temperature. So we have a function of temperature, right? So
Right.
somehow we're getting a linear function that is just a function of E is somehow becoming a function of E and T.
Does temperature affect irradiance?
Irradiance affects temperature, but it is not the only factor that affects temperature. There are
Okay.
other factors that affect it as well.
Okay. Um.
So,
Yeah. It.
so what I see, Jaden, as the solution to this problem is that each one of these lines, right, should have a constant A1. That
Right.
A1 is determined by a specific temperature. So my theory is that this right here is our A1, but it has to be at a specific temperature.
Um,
And I can tell you why I believe that. There's another
okay.
equation that states this, and this one you'll see is why I like this equation a lot more. So we have power, and this is actual power, okay, so this is reporting power, is equal to
Okay.
E in parentheses A1 plus E A2 plus T A3 plus W A4. Now that W stands for wind. Okay?
Okay. Where did you get this equation?
This equation comes from the standards used to normally test solar arrays to make sure that they are functioning how they are supposed to.
Okay.
And this one has all sorts of references to
Okay.
where this comes from. Now look, Jaden, I wanted to show you something really beautiful here. What happens if E is 0 in this case?
Yeah, your power is 0.
That's really nice, right?
It sure is.
Moving forward, here's our temperature, and it has its own coefficient next to it, right? So this means that the temperature affects it in its own way. And then this is wind. And so the idea is that the wind also, because this is, anyways, this is the wind affects it by cooling it down, essentially, right? So it also has its own coefficient in front of it. So this way, you can create all these separate lines, right, by changing your temperature or changing your wind.
The wind. Okay. So so with all of this, the company's goal is to get this power adjusted to try and label their solar panels as, hey, this is our power adjusted. This is where around how much energy you should be receiving from the solar panels. Is that their goal?
So the goal is to prove that the solar system, solar array, is working the way it's supposed to, right? So that's the goal. And normally, in most situations, this is the equation that is used for that. I have never seen this equation.
Yeah, what?
And so my thing is, I'm tempted to go and tell them and say, hey, this equation does not work. It is not a real equation. But I want to make sure that I can say that. And I just, looking at it.
Know, where did it come from? Where did
I have no idea. They have zero reference, Jaden. Zero reference to it.
And do they give you notes?
No.
Hey, Kip, here's an equation. Here's some notes that we were thinking about.
Nothing. This was in the contract. I don't know. Maybe I'm spilling too much on the live web, but I don't think many people are watching. So.
Okay.
So
Did you Google that equation?
I have not Googled that equation. Maybe I should. But here's my biggest concern, Jaden, right? So according to this, power adjusted is going to be a function of E, right, comma T. Okay? And this is somehow equal to an equation that is just a function of E.
Okay. Let me go back. So it's a function of, you said E and T?
Right, because we've decided that power, the actual power, has to be a function of irradiance.
Yeah.
And it's also a function of temperature. It's stated that.
Temperature and wind too, right?
Well, that's this one down here. This is a, so just, yeah, that one does not. Ooh, nice laser.
Thanks.
Oh, Carsey's got some good Spanish going on there.
I don't know if Google's gonna know this equation right off the bat.
Yeah, I don't. I would have to. Anyways.
Okay, so I'm looking up some stuff on Irradiance. So,
I agree with you 100%, Carsey. This math is garbage, so maybe we should just move on, Jaden.
yeah,
Unless,
I don't think they I don't think they thought through that equation before they sent it to you.
I don't think so either. And unless there's some article that they have reference to stating where
Yeah,
they got that equation from, if there's some article, then I'll believe it. But until I get that article,
yeah.
I mean,
So
just what I've
I
learned in math, this equation can't be true. So,
I've looked up like irradiance, and it's like it equals partial derivative of the radiance flux over the partial derivative of the area. So it's like
right.
that. It's just like that makes sense, right?
Right.
But yes, that's not.
It doesn't make any sense. I feel like they just threw
Yeah,
two equations together and said, yeah, they equal each other.
yeah,
But
and
there's,
I'm still confused on even if like the temperature minus RC, if you have a negative number, then you get a negative power. Like that doesn't.
exactly. Jaden, this equation is, that's why I like this one so much more.
Yeah,
This one makes
this one.
sense.
Yeah,
Because there's no way to get a negative power. And when your radiance is 0, your power is 0. It makes perfect sense. And it takes into
imagine.
consideration temperature. It takes in consideration all these different factors and has all these different constants.
Yeah, imagine like selling your solar panels and be like, hey, just so you know, you might get a negative power, meaning it's going to use your power from your
Yeah.
house. So just know
So,
that.
but also there's a possibility if the sun isn't shining, you still can make energy. So it's a trade-off. You choose.
You're like,
Because that
those stars, we can get some energy from those. Yeah,
uh,
I don't see what they were thinking,
I
but
can't
maybe they're
either.
a lot smarter.
They'd have to be a lot smarter. Um, so Jaden, does this get your mathematician stamp of approval that this does not equal this?
Yeah, I think so. I
And
would.
my logic of saying that one is a function of two variables and one is only a function of one variable, I feel like that's pretty sound logic, right? That
Yeah,
one,
especially to make like a linear equation out of this.
right. You can't do it. A1 or
Yeah,
A2 must not
like
be
really
constant,
be
right?
doing.
Either they mainly A1 could not be a constant.
Yeah,
A1 would have to change with temperature in order to make this exist.
yeah,
Cool. Thanks, Jaden.
yeah.
Well, maybe they wrote down their equation wrong or something. Thanks, guys, for watching us work through that and come to the conclusion that people apparently don't know math.
Yeah, we needed I think a little bit higher math than like a linear equation to deal with something like that.
Yeah. Or at least a multivariable, right? Linear
Yeah,
equation of some sort. because just claiming that it's a linear equation is... Anyways.
Yeah, that's...
Okay, well, good thing. So when I turn in my report, I can tell them this, and hopefully I don't get chewed out. But
yeah.
my guess
Maybe.
is someone read. My guess is someone read that standard, and they pulled that equation kind of like from knowledge that they knew, and kind of just were like, yeah, this works.
Yeah, probably.
Okay.
Mhm.
So, what do we want to do for the rest of the half hour that we have? Anyone got any suggestions? All you people watching, all you lovely folks.
Yeah, you guys want us to talk about something that you understand and
Jaden, that's rude to make them assume that, or to assume that they didn't understand.
well, I'm
Our
just going off.
viewers are smart.
I'm just going off the comments. That's all.
Dude, they just said their brains hurt. That doesn't mean that they didn't understand.
Oh, okay. Sorry, I apologize, everybody that has typed in the comments. Forgive me and give us a question.
Boogie. I don't know what that means.
Uh,
You want us to dance? Okay.
so,
Jaden, should we start? We could briefly go over some very, very basic physics.
sure. Are we
Starting
on
off with,
slide
I'm on
2?
slide 2 now, yeah.
Okay.
Let's see if we can explain very basic physics concepts and ways that people understand. Why do avalanches happen at 35 degrees of slope angle and not 30? Ooh. Should we go for that one, Jaden?
Yeah. Good question.
Okay, that is a good question. And it's a good physics question. Boop. Boop.
Yeah.
Whoops. I
Dude,
messed up on my
nice.
triangle. I messed up on my slope.
It looks decent.
Okay, here we go. Boop. Boop. Dude, do you think that's about 30 degrees?
Dude, just write 30 in the corner and then I'll believe that it's 30.
This is my corner, right? This is the right corner, I believe. I always get
Yeah.
confused with, yeah. So my
Yeah.
slope is 30 degrees. All right.
Yep.
So, and then we're going to draw a second triangle.
Ooh.
Ooh. It's got to be a little taller. Ooh. This is a little exaggerated. And this is 35 degrees. All right. So Jaden's going to be skiing on the 35-degree slope. Draw yourself. I'm skiing on the 30.
Okay, I'm gonna draw it myself.
Woo.
Ready? Wee! Wee! Skiing! Whoa, what happened there?
Dude, you got big skis.
Okay. Whoop, whoop. Yeah, I'll draw the ski poles. I like that idea. Whee!
Okay. All right. So we got the snowpack down here. Boop. Snow. All right, Jaden. So, why do you want Jaden to get caught in an avalanche? I didn't. He's just the experimental tester for the 35-degree slope. We'll see what happens.
It's because
Wink,
I'm
wink.
invincible.
It's because Jaden's a better skier than me. He can out ski the avalanche. Okay. So, Jaden, I'm going to do something here, which is gravity, no matter where you are, is always pointing straight down. So even though there's a slope, gravity is pointing straight down, okay?
Right.
And we'll note gravity with the force Fg, all right? So for any of you guys that have been watching, force of gravity is the mass of an object times the acceleration of gravity. And so so in this case, the snow has weight to it, or it has a force of gravity to it, okay? But the thing is that when you're on flat ground, right, this force of gravity is coming straight down like this, right? And then you have a force of gravity going straight up like this, which is the normal force, okay? So that's the total amount of force. It's being pushed back up. It's keeping it from falling, all right? So in the case of a slope, you still have the same thing, but the normal force is perpendicular to the slope still, okay? So you've got the force of gravity going straight down, but the normal force is perpendicular or at a 90-degree angle still to the slope, okay? All right, so we're gonna draw some triangles here. Boop, 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 boop. Boop, 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 boop. Boop, 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 boop. Okay. I always get super confused on these triangles, so let's see if Jaden can help me out.
Are you trying to figure out is the...
I'm trying to figure out where the 30-degree is.
It is... Wouldn't it be this corner?
Yeah, I think you're right.
Is that what you're thinking? I don't know. That's what I think. I could be wrong though.
Okay, well, this is the hypotenuse. I may have done this wrong. I always get confused how I have to. I like the pen sound effects. Gee, thanks.
Boop, 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 boop.
Yeah, I think it's like this. And then, so this is this 90 here. No, I think this is the 30, isn't it? Right? Ugh. I get so confused with my triangles.
Let's see. Because we're trying to have similar triangles.
Well, let's think here. So as the cosine gets bigger, it becomes smaller. So, no, you're right. It is that 30. Is this one. Okay. All right. So if we're trying to figure out what this normal force is, N, okay, that normal force is equal to is going to be equal to the force of gravity times cosine of theta. Okay? Where theta is the angle of the slope. All right? Is that making sense, Jaden?
Yeah.
Okay. So the normal force, right? So if this was completely flat, if theta equaled 0, then cosine of theta equals 1. So the normal force, or the force pushing back up, right, it would be this situation right here when theta equals 0. the normal force would just equal the force of gravity, right? But as it starts to slope down, that normal force isn't as strong because now the slope is changing, so the force of gravity is kind of, there's not as much, I'm trying to figure out how to explain this, but there's not as much force directly on the slope. Does that make sense, Jaden?
Yeah. So the force of gravity is pointing you down, but since you're on a slope, it's the normal force is counteracting it, not
Right.
completely with gravity.
Right. So if we had a slope of 90 degrees, so if theta equaled 90, right?
Right.
We're coming straight down like this, right? And so at this point, there is no normal force because there is no force in the horizontal direction, right?
Yeah. Right.
Okay. So what happens is, Jaden, as theta gets bigger, our normal force gets smaller.
Right.
Okay?
It gets less and less.
So another important thing to add in here is that the friction force, okay, which is pushing us back up this hill, our static friction force is pulling us back up this hill, is equal to the normal force times mu, which is the coefficient of friction. It's just a number, all right? So as the normal force becomes...
for each surface, right?
Yeah, it's different for every surface. It changes for every surface. So as the normal force gets smaller, right? So as n gets smaller, our force of friction gets smaller.
Mm-hmm.
So Jaden, what's going to happen as our friction force gets smaller?
As the friction force gets smaller, that means you're going to be going faster down the hill, and it's going to be easier to actually go down the hill because the force of gravity is becoming the main force acting on you as all the other forces get less and less.
Right. So yeah, so you have less friction holding the snowpack back up the mountain, right? And so the force of gravity is pulling it down the same, but there's less of a normal force, so there's less friction holding the snow back up, right? And so it's able to more easily slide. And then we've got a comment here saying, interesting fact for this lesson, avalanches rarely happen at slopes steeper than 45 degrees for the reason you just explained. So once it gets past 45 degrees, there's such low friction force holding that snow on that it actually can't stick, right? It just slides down.
Immediately, yeah.
Immediately, yep. So did that answer the question? Please let us know. If you need us to go into more detail, we can, or try to clarify something, let us know.
At 35 degrees, it packs and it packs and it packs, and then eventually it gets too heavy and it causes the avalanche, right? If something disturbs it or whatever.
Yeah, so sorry, keep going. Yeah. So the other thing, Jaden, is that we have this, I'm going to draw on yours here. So you have friction force going up, and then you have the force of gravity that's at that angle pushing it down, right? So at that angle, so it's going to be F of G sine theta, okay? And so as it goes down, that force of gravity is pulling stronger. So not only is our friction force getting less, but our force of gravity is actually getting stronger on the slope, right? And so as the snow builds up more and more, it gets heavier and heavier. And then all of a sudden we got Jaden the skier that comes skiing down, and
That causes the avalanche.
all of a sudden he puts enough extra weight or he breaks something loose, changes that static coefficient of friction, and all of a sudden, boom, it goes.
Yeah.
So that's why you want to ski on not as steep slopes. Or you want to ski on really steep slopes.
Yeah.
But it's also why skiing at 35 degrees is so fun, because the friction force is less, you have a strong force of gravity pulling you down, but it's not so strong that you're gonna
But
just die. Ooh, poor Jaden. Yeah, Jaden didn't pass the experiment. He collapsed in an avalanche.
yes. Poor me. Oh. Great question, though. Thank you.
Yeah, thank you. That was a very good question.
I think
Jaden, you
solved.
can. Oh yeah, solved. Did I? Oh wait, I hit him. I hit it. I forgot. I gotta unhide it. Solved. And mathemagical.
We
Jaden,
have
you
a
can answer
question.
this question.
Why do you guys think math is fun? I just don't comprehend when people ask me that. I don't understand why people don't.
Yeah, why don't you think math is fun?
Yeah, it's so at a certain level of math, when you start seeing like proofs and just higher math, it just becomes this beautiful thing where you just see this like truth happening all around you.
I would have to agree with you. One of the most amazing experiences in my life was learning about Maxwell's equations and how light works. And it was just like this most beautiful thing that I don't know how to explain because it was just so mathematical. So,
Yeah, you need math to explain it. Like you
yeah,
don't explain it in words, like you just use the math to explain it.
yeah. And when it comes together, you're just like, whoa.
Uh-huh. Yep.
So we got another question, which is why do I get shocked when I walk on carpet and touch something else? Um, Jaden, you want to take this one?
So when you are walking on carpet, you are basically charging yourself.
But why?
Why does this happen? Uh, so there's positives and negatives, right? All your atoms, whether the floor is positively charged or negatively charged, you start forcing all of that charge, the opposite charge, to like the extremities of your body. And then when you touch something that's like oppositely charged, you send a little jolt through yourself.
Little jolt?
Yeah. Uh,
Yeah, I
yeah.
mean, so your body is not what we would consider a great conductor, right? It doesn't it doesn't allow current to flow through it very good. Um, to some extent, it does, but not great. And then if you're wearing shoes or something, that makes it a lot worse. And so there's kind of like in a carpet or other things, there's a lot of these carpets aren't great. Uh,
You
what
could
is
do
inside
balloon.
the little
Yeah.
jolt? So if we have, if we have carpet, right, this carpet can have a whole bunch of what we'll claim as freestanding electrons on it, all right? So let's say that this carpet, for whatever reason, has
Change
electrons
slide. Yeah, you did.
chilling on it,
Sorry.
okay? What?
Okay.
Boop, 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 boop. Okay.
Dude, that
And
looks like my birthday cake.
dude, are you how many years old?
Negative, negative, negative.
Negative. Okay, so these are all electrons chilling on there, all right?
And electrons are negatively charged.
Yeah, they're negatively charged particles. They could be protons, but we're going to go with probably more than likely electrons. There's not as many freestanding protons just chilling out there in the world. At least that's my understanding. I could be wrong. And so, Jaden, here's my foot. Boop. Okay. And this foot, as it walks over, these electrons are kind of stuck in this carpet, right? The carpet is not a great conductor either, right? So these electrons just kind of get stuck in the carpet, all right? Well, then my foot comes across the top and kind of rubs against it.
And
these,
opposites attract each other.
yeah, so these electrons get stuck, right, to the bottom of my foot. Boop.
Wee, wee, wee.
So now I've got all these electrons, okay, on the bottom of my foot. Boop, boop, boop. Dude, I look like I've got roller skates now.
That'd be a really cool roller skate.
Yeah, it would.
I'm like, how many of those wheels would actually work? Okay.
I don't know. Okay. But then those electrons don't just stay in my shoe, okay? They'll kind of disperse throughout my body eventually. But because my shoe and body are a good insulator, it doesn't deposit those charges back down into the carpet, all right?
Yeah, you're just getting more and more as you are dragging your feet across this carpet that has all these loose electrons going on.
So now let's say I go to the fridge, right? The fridge is metal. So guess what metal is, Jaden? It is a great conductor.
Yes.
Okay. So
that's why it always happens when you like grab a doorknob too.
Yeah, doorknobs, anything like that. I'm using the fridge because this happens all the time at my house. I don't know why, but it does. The fridge in particular is bad news for me. And so I go to the fridge and I'm now negatively charged, right? Because I've got all these electrons. I'm so negative, dude. Maybe that's why I get depressed, is because I got too many negative charges on me. So in comparison, right, this fridge is now positively charged in comparison to me, right? This is one of the most important things about electricity in general, is it does not matter whether or not something is positively or negative charged actually. It's just in comparison to another thing it's interacting with, right?
Right.
So in this case, I am more negatively charged than the fridge, all right?
That becomes your positive.
So that becomes my positive, and the second I touch this handle, all those electrons in my body want to go to this fridge to equal things out, all right? So all of a sudden I've got these electrons, boop, 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 flying out of me to touch that. Now, part of the thing is too, is that there's an electric field that builds up right here on your finger between you and the fridge, right? And so that's why, so once you get close enough, those electrons will actually hop. They'll break down the air around you and hop. And that's the spark that you see, right? That's why you don't have to actually touch it.
Yeah, it's a little jolt. But the jolt is electricity.
Yeah. So the question is, but why? What is inside the little jolt? It's normally a whole bunch of electrons leaving your body very quickly, and those electrons have energy associated with them, and that energy is what you feel as it's leaving your body. And that's why it hurts.
Dude, what if you were so negative that even the positives didn't like you?
Dude, then I think physics would break.
True.
So there we go. That is that question answered.
That's the same thing with balloons. If you rub it on your hair and it like sticks to you, it's because of the charges between the balloon and your hair,
Yeah, exactly.
or it, or the wall, or whatever you do with the balloon.
Jane, I want
Pretty
to see
cool.
you. Do you have a balloon by you? Let's see you do it right now.
I do not have a balloon by me.
But why?
I wish I did.
Okay. Well, should we end 5 minutes early and say thanks to all of our viewers for
Yeah. Did
why
that
do I
answer your question? Kip did an excellent job explaining that. Why do I get shocked on the
on the
cement
cement
floor at
floor at
Sam's
Sam's
Club?
Club? I,
Dude, you
I
must be
need
a
a little
plumber.
more explanation to what that question is asking. Do you get shocked when you walk on the floor, or do you get shocked after you walk on the floor and touch something?
Or are you shocked, like emotionally?
It's just so beautiful in Sam's Club that they get shocked.
Oh, that's a good question. Why do the hairs spread apart when you rub the balloon? So all of
Jaden,
your
you can.
hairs have the same charge. So if they were positively charged or negatively charged, that means they don't like each other at that moment, right? Same charges repel each other. So that's why they would spread apart, but attracted to the balloon. Does that answer that question?
Yes, that does. I think so. I want you to draw a picture, though.
Oh, picture.
Yeah. And while you're drawing that picture, I will. Carsey gave us a little more information. It says, I just walk there, and whenever I touch anything or anyone, sometimes I'm shocked emotionally too. I love the product there. So, yeah, it's the same deal. The cement floors
That's
there
the
probably have a charge building up on them. And so when you walk on it, you pick up. Nice. Nice balloon. But when you walk on it, on that floor, the charges get on your shoes, same deal, and they break off. The
yeah.
concrete floor just builds up charge over time, and then you pick them up when you walk on it. All right, thank you for that nice comment saying that it was a nice lesson tonight. So thank you guys for that. We will be signing off here. Please don't forget to like and subscribe, and